Hello everyone. A very good evening. I welcome you all to this live session, the first live session of the PH01 course from NPTEL SWAYAM, a great initiative. I, as you all know, that this course is being taught by Professor Saurabh Basu from IIT Guwahati, and I would like to introduce myself a bit also. I am Shani Burman. I am a fourth year PhD student in the Department of Chemistry from IIT Hyderabad. Um, so I am pursuing my research in solid state chemistry. It basically comes under a broader spectrum of inorganic chemistry. And during my PhD work, I have synthesized a lot of materials which are superconducting in nature. So I do have uh, a knowledge of superconductivity and all. So uh, this course is very useful for me as I have also earlier I have learned from the video lectures, and I hope as this time I have been chosen as a TA, I can give justice to that, and I will wholeheartedly I'll try to solve your doubts and guide you as you want. So yeah, before starting the class, I would like to know if you all are from this similar background, like physics or chemistry, or know like a very little much about superconductivity. If not, there is no problem. Of course, I'll go through. But if you let me know, it will be very helpful. Do text to leave your chat text in the chat box. Now, so in today's class, what will you do? We will first go through the whatever the lectures, the three lectures sir has taught in the first week, and after that we'll go through the homework zero, because homework one is pending. It is, you have to submit it by 5th of February. I hope you all know how to submit the assignments in the website. If you don't know, do let me know so that I can show you. If you know, that's fine. You can submit the assignments on time. Yeah. Okay. So since homework one or the assignment one is due, we'll be discussing today about um homework one, homework zero or assignment zero. Okay. So before starting with assignment zero, I would like to go through a brief outline about what sir has taught in the first week. So, okay, let me write first the title, uh, brief course on superconductivity. So first, we'll go by outline what sir has taught in the first week. Then we'll go through the homework zero. Okay. So superconductivity. Yeah. So we would like to start with the discovery or the history of it. So superconductivity, it was discovered by Professor Kamerlik Owens in 1911 by taking the element of the as Ag, the only mercury. Now, why he has chosen mercury? Because mercury is of high purity, and it has low melting point, almost. minus 39 degrees centigrade. As we have already seen in thermometers, there are mercury inside, and if by chance you break the thermometer, you can see that the mercury will be in like a round ball shape, and it will be free flowing on your like uh, tiles. So mercury is very like in a liquid form. It stays in liquid form in room temperature, and it has a very low melting point. And so you can say that it remains liquid in liquid state over a wide range of temperature, allowing it for easy cooling and solidification, of course. At like and it is very requirement, like it was one of the requirement for cryogenic experience. Cryogenic means where low temperatures is required. Okay. Now the another thing is of course the availability is it is one of the metals which is available in high purity form. Okay. And it has very simple electronic structure, and so that theoretical interpretations are easier. Okay, so what did he observe, like in his experiment, Professor Keown's, that he has discovered superconductivity out of a metal. So when he was doing an experiment, he cooled to around 4.2 Kelvin, cooled. Now the electrical resistance of mercury dropped to zero, like suddenly. So there he saw that, okay, this is if this is electrical resistivity rho, this is T. He saw that this thing is abruptly like till here, s- till here, it was coming in in certain slope, and here it has dropped suddenly up to this temperature. So this is 4.2 Kelvin. Okay, if it is in temperature in Kelvin, and this is resistivity. So that's how he discovered superconductivity. He observed this phenomena, and he has said, okay, something is surely happening. Now, how we can how we can discriminate between the magnets and superconductor. So a superconductor is like exhibit perfect diamagnetism, while magnets exhibit spontaneous magnetization. Okay, of course, due to the alignment of atomic magnetic moments, or the spins, what we call. So you all know that. You all have must seen magnets, right? So magnets are such as, and if you make two magnets come close, like make them come closer, it will of course the both will attract each other, right? So that's how like magnets exhibit spontaneous magnetization due to their alignment of magnetic spins, right? Now, this magnetization persists without any external magnetic field. No external magnetic field is needed for a normal magnet. Like we can give examples like ferromagnetic materials like iron, cobalt, nickel. And you already know that what are paramagnetism, diamagnetism, ferromagnetism, ferrimagnetism, antiferromagnetism are there, right? So you should have the basic idea of those, because for those terms and those terminologies, those principles are very much like gonna be relevant with this course. Now, ferromagnetic materials like iron and all, at least you should know that what are paramagnetic and diamagnetic, right? So, in paramagnetic, there must be one what's say unpaired electrons, but for diamagnetism, it's already paired. No valential electrons will be there. Now, these are the examples of normal magnets. Now, what are superconductors? So, superconductors they exhibit perfect diamagnetism. Superconductors this is perfectly diamagnetic. Okay, these are perfectly diamagnetic. Let me just check whether this is recording or not. Yeah, it's recording. Okay. Now, yeah. Now magnets, yeah, what I'm telling about superconductors. Superconductors are perfectly diamagnet. Huh? Now there is a, why this is a diamagnetic? There is a term comes Meissner effect. Meissner effect. Okay. Means this basically tells about the expelling nature of the magnets, superconducting magnets by external magnetic fields. When external magnetic field is present, the superconducting whatever the material will be, as like which is acting like a superconducting magnet, it expels the external magnetic field, right? That is the Meissner effect. Sir has also taught this in detail in the lecture. You should go through that. And unlike magnets, superconductors do not retain magnetization. Okay. Once the external field is removed. Like for magnets, if you remove the external field also, it contain a little bit amount of magnetization, but superconductors do not. Now, this diamagnetic property of superconductors is due to the Cooper pair formation, right? Um, so there are all this also one. This is very popular and important term in this course, which is Cooper pairs. Right now, we'll learn about the Meissner effect. So, what happens? Like if there is a magnet, this is the material, okay, and there is one magnet. Okay, I'll just draw separately also. Let's say, yeah. So what happens for Meissner effect? There is an expulsion of flux. Means flux don't go through that. Don't like penetrate the magnet, right? So what happens? The Meissner effect is expulsion of magnetic fields from a superconductor when the transition temperature is below its critical temperature, right? So below critical temperature, which is also known as TC. C stands for the critical, and the a superconductor mean material. A superconductor expels the magnetic fields. Okay. Now, this effect is independent of how the superconducting state is reached, right? So, proving that superconductivity is not just perfect conductivity but a fundamentally different phase only. Okay. So, like what we can tell that inside the superconductor, there is B equals to 0. B means magnetic field. There is no magnetic field. Like nothing is, no magnetic field is penetrating. No magnetic field penetrates, penetrates the superconductor. Right. So, what happens? Uh, so like a magnet levitates above the superconductor due to the Meissner effect. So if we can draw this magnet here. So this magnet levitates, okay? So levitates. So superconducting phenomena is also a levitating phenomena. Superconducting phenomena or superconductivity, I'll rather write. Superconductivity is a levitating phenomena. So this is because, of course, like perfect expulsion of the external field, and there is one type of semi superconductor which also allow partial penetration, right? Partial penetration of the external magnetic field, and this cause a stable levitation. Okay, so for stable levitation, due to partial allowance of penetration of magnetic fields. Also, here flux speeds, right? Uh, okay. So, using this technique, Japan has also, they have come up with that idea of maglev trains. So, this is a very new cutting edge research nowadays. Maglev trains in Japan. So, what do they do? They apply like the tracks and on the or the on the like trains, the superconducting magnets which make the trains levitate. Right, if on the trucks there are superconducting magnets, it will, and a magnet on the like bottom of the trains, then it will make the train levitate, and this helps to reduce the friction when the like normal train in our country like as the functions. So this is, and due to that the this frictionless motion, magnet trains are very fast. Okay, so it like the speed has enhanced, and like technology has been served. So it is a big deal for the superconducting science community. Okay, yeah. So like that, like this type of applications can be done further also, like to reduce wear and tear in the like high speed applications. Now I have mentioned here TC, right? That means transition temperature. We call it, or the critical temperature, right? This is also known as transition temperature. One sec. Transition temperature or critical temperature, or TC. Now this is the critical temperature below which a material below which a material like enters into the superconducting states, showing zero electrical resistance. Means zero electrical resistance means, what is the opposite of resistance? Conductance, right? So inside it, the continuous conduction is happening, right? And perfect diamagnetism. Superconducting means that's basically right. So what I was talking about resistance. So V equals to IR is the Ohm's law. Okay. And where for and when the conduct R is the resistance, right? And also we mostly we call superconductivity, mostly we detect in the terms of resistivity. That is rho equals to L by A. right? Now, if conductance or conductivity is there, then it will be the opposite one. Like it's the basic things, and also we know that any from like for superconducting experiment. Since I have done, I am telling that like we detect the resistivity, right? And but first we detect the normal room temperature VI. VI means VI, which gives R. Now the slope or the tangent will be here. This value will be the ohm, right? So this is the thing. The VI plot should come linear so that we can detect the R value from it. Now above TC, above TC, this is below TC, right? What I'm talking about. Now this plot you can solve. You can see that this one you can see that this is above TC, right? If we take if we take 4.2 as TC, then this graph is above TC, this yellow colored one. Now, above TC, material acts like a metal, like metallic in nature, as you can see. And how can you prove that? There only I have shown that it is rho by T, right? Means resistivity by temperature. Like dependence of resistivity on temperature. Now, for a metal, if the temperature rises, the resistivity is increased because of the free electrons, right? So that is, and due to that, electrons, like they collide much and they become resistive. Right, the conductivity doesn't happen quite so easily. So, like for metal, it is mostly as the temperature increases, it becomes metallic in nature. And for superconducting, for the same, above TC it's metallic in nature, and below TC it's superconductor, becomes a perfect superconductor. Right. Now, what happens near TC? Right, when resistivity drops to zero. This is above TC. This is near TC. There resistivity becomes to zero. In the if in the y-axis there is rho, then resistivity till let's say this temperature resistivity was something. But like as it is like reached this such temperature, it becomes the resistivity becomes zero. Zero here it is zero. Right. So what happens that below TC the electrical resistance suddenly disappears. Now this material expels the field, like perfect magnetism as I have told. Now Cooper pair forms. Earlier also I mentioned this term, Cooper pair. Cooper pair. So what happens in Cooper pair formation? So below critical temperature, electrons form bound pairs due to phonon mediated interactions. Right. Now, you may ask that what is the difference between the phonon and photons? So, photons are basically the particles from the light, and phonons are basically the particles from inside the atom, right? So, what happens? Phonons are the charge carriers. So, what we told that if, yeah, so if, let's say if one, what I can say that if there are electrons, and phonon is interacting with each other, then this electron is become a little like del positive and it can interact with another electron, then it can form the pair, like as a pair, a plus minus becomes a pair, right? Like that only. So in lead, we can give example as we have already given for mercury is 4.2 the Tc. For lead it is 7.2 Kelvin. Right. Also in like near the Tc or the transition temperature, superconducting energy gap appears. Superconducting we can write it as a delta energy gap that prevents electron scattering. Means if electrons are scattered, then it won't form. It will be hard for them to form bound pairs. So electron scattering is not preferable. So this prevents electron scattering and electron scattering and ensures zero resistance. Also, there is one role of the specific heat, right? So a sudden increase in specific heat also happens. It due to the like second order phase transition. As I have already just mentioned earlier that due to this formation of this Cooper pairs, the macroscopic quantum phase like coherence happens. So it becomes of another phase the material. So that's what I'm trying to say again. At transition temperature, there is a sudden increase in specific heat, indicating the second order phase transition. Now, like I have already told, now I we can discuss about the Fermi surface, the energy gap I have mentioned, right? So Fermi surface, like what happens near Fermi surface? Why superconductivity happens near Fermi surface? So the Cooper pair formation happens. It involves near electrons from the Fermi energy, like which is the which electrons have has a Fermi energy. Those electrons only involved in Cooper pair formation, right? So the Fermi surface is a representation of of electrons with highest occupied energy levels at absolute zero. So what does the energy gap means? The energy gap in the superconducting materials, they form around the Fermi surface, affecting only the electrons with a narrow range. Means near the Fermi surface there are electrons, and these electrons only gets engaged to form Cooper pairs. So this electrons only contribute to superconductivity. Now, this is superconductivity happens in low temperatures because only a small fraction of electrons we can find in near the Fermi surface, which ultimately participate in Cooper pairing, right? So, but like right now in the like literature, there are mostly low temperature superconductors are available. Like so, people are very much curious to make or synthesize the high temperature superconductors. Those are very in like a hot topic in superconducting science area. Now, there are like I have already told that the normal magnets act as ideal conductor, and superconductors are a little different. So, no, for normal magnet, they don't show like zero electrical resistance, right? But an ideal conductor, if you can take an ideal conductor means no resistance should be there, zero. So you can say that is a superconductor is an ideal conductor. No, even if they both has zero, like they both have zero electrical resistance, but magnetic fields is only expelled by the superconductor, not by the ideal conductor. So superconductors, I can write it by SC, okay? is not equals to the ideal conductor, because this do not expel magnetic fields, by whether superconductors do. Because in if an external field is applied before cooling, it remains trapped inside, right? So for ideal conductor, if you apply the external field before cooling, it remains trapped inside. Okay, I'll write also. Hello. Yeah, I hope I'm audible. There's something pop up in the screen. Yeah, I'll just rejoin since this this something happened, and this is showing that um it's not like I can't share the screen. The screen is not visible. Uh, so now what I was talking about, yeah, the magnetic field gets trapped inside the ideal conductor. So now we are already know what we know till now. We know that what is superconductivity, what is Meissner effect, what are the Cooper pairs, how do they form, where they form, and the difference of superconductor with a magnet and an ideal conductor. Right. These things we know. Now, of course, the one thing I can also add that to superconductors, we know that it's perfectly diamagnetic, but the ideal conductors are not, they don't give any diamagnetic response. Okay. Now, coming to homework zero. So, the first question is schematic plot of resistivity versus temperature for a normal metal and a superconductor, that we have already mentioned till now. So the first question is normal metal, as I have already told, the resistivity increases with the temperature. And for superconductor, it decreases at a certain point, which point we know as EC, or the critical temperature. This is normal metal, right? Metal is last, yeah. And this is superconductor, right? Yeah. Now, the second question is, okay, I can draw it below. So the second question is schematic phase diagram, magnetic field versus temperature for type 1 and type 2 superconductors. Yeah. Type 1, there are two types of superconductors, type 1 superconductors and type 2 superconductors. So type 1 superconductor, as I've already told, that those are perfect superconductors, means they don't allow any magnetic fields to penetrate them. Whereas type 2 superconductors, they partially allow. Now, type 1 superconductors, they exhibit only a sharp transition between the superconducting magnetic field. One second. Yeah, just a sec. Yeah, I hope it's recording. Yeah. So the for the second question, so type 1 superconductors, it exhibit a sharp transition between the superconducting and the normal phases at a critical magnetic field also. Like this like phase with this plot we'll get at a critical magnetic field. Critical magnetic field, we denote it as H and C for critical, right? This is for type 1. But for type 2, there are two type 2, there are two critical magnetic fields, HC1 and HC2. Now, when H is okay, I'll just draw the phases, then it will be easy for you to understand. See, this is the plot, this is the TC, and if it is the magnetic field, then this is the HC, and mm, this is type 1, right? So inside it, it is B equals to 0. Now, when H equals to HC, for where should I write? When H equals to, this is what type 1, right? So I should draw that type 2. Since type 2 has two type of critical magnetic field, one is HC1 and one is HC2. This should be one, the lesser one. HC2, HC1. Yeah. So what happens here? It is B equals to totally 0. But here in the mixed state, or we also call it as a vortex state, here B is not 0. B means like magnetic field inside is got penetrated. Right. So for H lesser than for type 2, H lesser than HC1, when it is the situation, the material is in pure superconducting state. Pure superconductor. When HC, like H is in between the HC1 and HC2, it is material enters in mixed or vortex state. Mixed or vortex state. Where magnetic flux, where magnetic flux penetrates in quantized vortices. Now, when H is greater than HC2, the material is in normal state, right? Means above this. So yeah. So in type 1, we can see only one single transition is at HC is happening. And for type 2, we can see there are two transition points, right? And a mixed phase in between. Here it is mixed phase. Okay. This here, the sir has asked you to draw. Then the third question is transition temperatures and critical magnetic fields of type 1 superconductors. Okay, they have asked. Okay, okay. So there are materials, aluminium, then the TC is here. EC and here is the HC. Sorry. So for aluminium, it is 1.2. This in Kelvin and this is in Gauss. Right. And it is 105. For tin, it is 3.7 and this is 305. For lead, it is 7.2. I have already noted down this value, and you can get it from any book or you can search for any literature papers. For niobium, it is 9.2, 2000. And lastly, for mercury, we have already seen 4.2 and this is 410. Okay. So can you just let me know in the next class that from this critical field value, which one you can say that why this value is higher or lower, or how can you analyze them, like which is better superconductor or which is type 1 superconductor or which is type 2 superconductors. Also, it has already mentioned in since there are no two critical fields, it's already type 1 superconductors that we already know. But yeah, how can you tell how is the dependence of the PC to HC? Dependence of DC or HC. This will discuss on the next class. Okay, and if please look into it. And the fourth question is Meissner effect and flux quantization about it is. So for the Meissner effect, as we have already understood that Meissner effect, we have already understood that when a superconductor is cooled below a certain temperature or the critical temperature Tc in presence of an external magnetic field, the magnet superconducting material expels all the magnetic flux, it doesn't like let them penetrate it, so each flux goes through outside of the superconductor. So this phenomena is different from perfect conducting material, right, as it is like implies a fundamental change in the material's electromagnetic response. So this one is the Meissner effect as and flux quantization. I'll just tell. So in a superconducting ring, the magnetic flux is quantized as like there is one equation phi equals to h by 2b, right? This is flux. This is the Planck's constant. E is the, of course, electron charge. Now this quantization arises due to the wave function coherence of Cooper pairs. Due to wave function coherence of Cooper pairs. Now the fifth question is magnetization versus applied a magnetic field for type 1 and type 2 superconductors, right? Now this one about the field, and this will be about the magnetization. So magnetization versus, and here the formula is M, this is B, M, B. Let's say this is for type 1 and this is for type 2. So type 1 superconductor, as we already know that this is a pure superconductor, they show complete diamagnetism until Hc, right? And after which magnetization drops to 0. So this is 0, B equals to 0 here. We can write as a BC for critical, and for type like this abrupt transition from superconducting to normal state at Hc, right? From superconductor, okay, let me just clarify it once more time. So for type 1 superconductor, it shows since it's the perfect superconductor, it shows complete diamagnetism until Hc. Hc means critical magnetic field, after which magnetization drops to zero. Okay, magnetization drops to zero M for magnetization, and this transition from superconducting to normal state, it implies the at Hc. And the transition from superconducting to normal state for type 2 superconductors, there are two critical fields, right? Hc1 and Hc2. Now, similar thing like this happens here also, but since there is Hc2 as well, so there is a gradual decrease to, sorry, this is BC since this x-axis is B. So BC2, and there since there are two critical fields, so this is affected by Meissner effect. Same for here. M effect I am writing. Okay, let me write the full name, otherwise you can get confused. Meissner effect. And the next one for HC2 one, it's about the mixed phase, right? So this much mixed phase, as we have already learned here. This mixed state, so type 2 superconductor, they show mixed phase where flux penetrates as vortices between Hc1 and Hc2. Right. Now, moving onward to the sixth question. Sixth question is that they are asking like energy gap versus the scale temperature. Right. So the superconducting energy gap, del T, del I we can write, it decreases as the temperature increases. So there is such equation where del T at certain temperature I am writing at del 0 root over 1 minus T by Tc. Right. T by Tc. So as you can see, the scale temperature means the whole T by Tc. So this del T, the superconducting energy gap, it decreases as temperature increases. And the phase transition is second order, right? Since a whole phase is changes happening, and since the order parameter vanishes smoothly at Tc, okay? So if you plot this del T by del 0 and T by Tc, so there is root over 1 minus something is happening. So this, near TC, it decreases rapidly. So this would be the slope will be sharp, right? Like that. Okay, this is near TC. Now, yeah, this is over. Now the seventh question is two fluid model of superconductivity. Now, the concept is superconductors consist of two coexisting fluids. Okay, one normal electrons, which is resistive, means they repulse each other. They're scattered here and there. And the next one is superconducting electrons, which are called Cooper pairs. Like they come up, they stay as in pairs, bound pairs, which are Cooper pairs, and they are formed near the Fermi surface that we've already learned. So the two fluid monomers, two fluid coexisting fluids. One is Normal electrons. Normal electrons means resistive and scattered. And the next one is superconducting electrons. Feature covalent Cooper pairs. Now, what is the temperature dependence of them? So, the fraction of superconducting electrons increases as temperature decreases. Means superconducting electrons, like I can write. Actually, basically, at T equals to that, at temperature equals to zero, all electrons are Cooper pairs only. All electrons form Cooper pairs only. Cooper pairs only. But as the temperature starts to rise, the forming of superconducting Cooper pairs process gets ceased. Now the eighth question is typical energy gap for a superconductor. So zero that is related to the it's related to TC, right? So for TC equals to 1.1 from 1 to 10 Kelvin, 1 Kelvin to take Kelvin, Kelvin, the energy typical energy gap or the EG, it is in the range of milli electron volt or 10 to the power 3 electron volt. Right. Let's say example are lead, which has TC of 7.2 Kelvin. This is in this range, right? So its typical energy gap is 1.2 milli electron volt. It's the same. Now the ninth question is specific variation across the superconducting temperature. So above TC, it follows the usual electronic contribution, right? Where CV equals to gamma T. But below TC, above TC. Now below TC or in the of course in the superconducting state, it exhibits exponentially to the power minus del by kBT. Right now, del is the energy gap, kb is the Boltzmann constant, and T is the temperature. And CV, what is CV? CV is the specific heat at a constant volume. Right. So at TC, there is a jump in specific heat. So how can we write CV at TC is very much higher at CV at TC dash, like some other temperature. So basically specific jumps discontinuously at TC. Then follows exponential decay. Like jumps, then follows exponential decay. CV and T. Now, the last question is isotope. What is the isotope effect in superconductors? So, at the transition temperature Tc depends on the mass of the lattice ions. Tc equals to m minus alpha, where alpha is the we take it generally 0.5 for conventional superconductors. Now mass with mass, right? So lighter isotopes exhibit a higher Tc, supporting the phonon-mediated pairing mechanism in VCS theory. VCS, as in Bonded Copper Cooper Schiffered theory. So this has also like sir has told like in the lectures you can find it very vastly say sir has explained. So please go through that. So by this analogy, you can tell that AG199 has a slightly higher DC than AG204. This is just one example. These are isotopes. These are two isotopes, right? So isotopes with the same um, uh, proton number, but with a different mass number. Okay, that it comes from proton plus neutron, right? So yeah, that was about the homework one. And in homework two, sorry, homework one I'm telling about. So in the homework of one also there is um some like something discussed about the Maxwell signing features of a superconductor. So we have already known that the features of superconductor is basically like zero electrical resistance. It shows Meissner effect, energy gap opens at Fermi surface, preventing electron scattering and ensuring zero resistance. Then there are Cooper pair formation due to electron phonon interactions. Now flux quantization I have already told. Now there is one uh, effect also which is called as Josephson effect. This one I have not talked about. Josephson effect. So Josephson effect is when two superconductors are separated by a thin insulating layer, a supercurrent can tunnel through, leading to Josephson junction effects. When two superconductors are separated by a thin insulating layer, a supercurrent can tunnel through. Okay, this is called the Josephson effect. Okay, now there is also penetration depth. The penetration depth and there like gives free energy. So I'll start. So I'll just note to jot everything down first. Penetration depth. Maxwell's equation gives free energy. Non-local electrodynamics. Then coherent length. So these are the things that we are going to learn about. And see this video is like is I'm recording this video, so I'll upload this video on YouTube. Now if you have any like doubts or since I'm going fast or like I'm not like a few things I'm not explaining in detail since will be running short like on time, so please let me know like where are your doubts, or should I explicitly explicitly explain everything, or we can just go like this only, like by touching the special topics only. So please do let me know, and on the next class we'll surely we'll Of course, we'll discuss the homework one and a brief, same thing, a brief outline about what Sir has taught, what Sir is taught in the second week. So now for now, we'll be doing the penetration depths. So please let me know. So it is the characteristic length over which an external magnetic field decays inside a superconductor. So basically, it quantifies how deep a magnetic field can penetrate before it is fully expelled. Let's say this much only. This much only. So this will be the lambda L. Okay.